Okay, if I could have everyone's attention. So Luke tells me that this quiz was the best quiz yet, and that for the most part, everybody did pretty well. There was only one that people had difficulty with, only one thing on the quiz. Let me just, and it was this one. And on the other side, we had this thing. Oh, I thought it was resonance, so that's okay. I'll have a very short arrow here. Okay, so this was a chemical reaction, and you know it's a chemical reaction because we have an atom that's moving. So it was an arrow. And then to push the electrons, so one of the things we want to get used to is for pushing electrons, we should start at one pair of electrons, and all our arrows need to go in the same direction. We should never have two arrows pointing towards each other or away from each other. And I still see some of that in some instances. So one of the things you want to remember, look at it after you've done it and see, do I have any arrows pointing towards each other or away from each other? So they may go in some array, right? But remember, you always start at a pair of electrons and end at where a pair of electrons end up. And in this case, so I think what happens is probably people use this pair of electrons to remove a proton, okay, and that's okay, but there's more going on here in terms of what I've indicated. The other thing is we're also seeing that we have a double bond here, right? And we have a single bond here. So we have to push electrons away from there. We have a double bond here, so we have to push some electrons to there to make that double bond. So you can actually push these electrons like this. Okay, that's making a double bond. If we make that double bond, we have to get rid of some electrons on the nitrogen. Otherwise, it's going to be more than an octet. So this reaction is actually quite simple once we get there. And then finally, that's the arrow pushing. That's simple, right? But one of the things you want to remember is you always start at a pair of electrons and end, oops, yes, I forgot a positive charge.
There's supposed to be a hydrogen after oxygen.
Oh, then I did it exactly the wrong way. You're exactly right. Okay, so, but I'm going to do it just the opposite now. I'm going to start at a pair of electrons. There we go. That's a lot better, isn't it? So, I had a late night, sorry. Okay, so I told you that I wasn't the best student, that I got things wrong because I wasn't careful. Okay? So, but you know what's nice is that you're catching my mistakes. Okay. So, but notice that I started here and all my electrons flowed. So I just have one long arrow that kind of goes like that, right? That's what you want to remember, is that the electrons have to flow from, and they'll start at either a lone pair of electrons or a double bond, and then they will finish, in this case, they finish as a lone pair of electrons on that oxygen. That's where they finish. Okay? But having said that, there were two I expected people to have some difficulties with. And the other one was where I did a retro Diels-Alder reaction, and I didn't leave your products like this. I left your products in their extended form. Okay? So people had to figure out a little one. And that was one where I don't know what we had, but it was basically this. Okay? So in this one, we have to figure out how are we pushing our electrons, and we could be pushing them this way. I could have pushed them the other way as well. But that's what we're indicating here is that, notice we're breaking this bond and we're breaking this bond. And Luke tells me that for the most part that wasn't a problem. So that's good. Today's quiz, unfortunately, when I had it printed, whoever printed it for me, their printer wasn't working correctly, and it actually, you have 2 pages instead of back and forth. Okay, so we'll have the quiz. While you're writing the quiz, I'm going to alphabetize your old quizzes. And when you pass your quiz in, you can pick up your old quizzes. Let's start today. This is where we ended last class. We said, how would we make this? I am trying to reiterate now. So this is something I expect you to know. Now, if you come to the exam and you're looking at that and you don't know, please feel free to raise your hand and ask. As I said, there's never stupid questions if you don't know. I may look at you and tisk and shake my head, and then I may decide to tell you. I may say, if I tell you, I'll tell the rest of the class, or I may say you need to know that. But don't be scared. I'll never yell at you that you should know that, okay? I'll just say you should know that, and then I'll feel bad. Probably not as bad as you. Okay, so how would we make this? What's the problem? Well, initially we might think, well, this is easy. This is just a Friedel-Crafts reaction where we use an alkyl halide and a Lewis acid catalyst, and we can make our compound. However, we've been told, and we're chemists and we're beginning to realize that we do know that when you have something that can form a more stable carbocation, it probably will. The major product, this would actually be the major product by quite a lot because it's the result of a tertiary carbocation that can form in the reaction. So this is not a good synthetic procedure to make that compound. A better one might be if we would look in the Aldrich catalog and see if we could get this acid chloride. And then if we get that acid chloride, we can do our Friedel-Crafts acylation reaction. And then we have to reduce this using either the Clemmensen or the Wolff-Kishner. The Wolff-Kishner we went through, and you should know the mechanism for that. It's one of the tougher mechanisms, I'll grant you, but it's not completely impossible as long as your electrons all flow in the right direction.
Would you be able to show on the board how it happens?
What happens?
Like the mechanism of how it can
Take a look through your notes. The Wolff-Kishner we did last semester. Okay, and so for this one we did last class. Okay, so take a look at your notes, or we can do it in the tutorial on Tuesday. And we said 4:30, right? Okay, I'll try and book a room. I'm pretty sure I can. Here's a nice problem for a quiz or midterm. Now that's a big indication that I might give a problem like this. Doesn't mean I will give this one. Okay, so here we go. For the following scheme, provide appropriate reagents above the arrows. Indicate whether they are needed in a stoichiometric or catalytic amount. This scheme is from your text, and as you may have guessed, I used the images from the text, and you can just destroy those little boxes to figure out the reagents, but give it a try. So this is Friedel-Crafts acylation reaction where we need a Lewis acid catalyst. If you look under there, you'll find a Lewis acid catalyst. So figure it out, okay? Figure out what you would have to do for this particular reaction. They are all reactions we have done, okay? So I like this. This I would consider a medium type of problem because you are going to have to remember a lot of reactions. I don't consider it real difficult. And you'll notice that, you know, it's easy to get. I mark all my questions out of 5. And then I'll look at them. I don't usually start off thinking I'm going to give half marks, but then I always do because the student always does something. I go, I think they know what they're doing, so I'll give them half a mark for that step. Okay, so, and then I would have to figure out why I would give you 5 here. You also want to be careful because even though the Lewis acid is a catalyst in this part, it's a catalyst that gets used up. So you do need a stoichiometric amount, and we did discuss that. Most times with catalysts, we don't need a stoichiometric amount, but we do in this instance because the catalyst actually ends up getting tied up by the product. The same with the last reaction. The next thing we want to talk about, okay, so we've been talking about electrophilic aromatic substitution reactions where we take an aromatic compound, which is our nucleophile, and it reacts with some electrophile that we form in situ through different ways, and we end up getting a substituted aromatic. What if we already have a substituent on there? Where will the electrophile end up? Is it just some statistical distribution, or is it more satisfying than that? Is it something that we would be able to predict and maybe use to design synthesis? I hope the answer is that it would be something more interesting. As you can guess, it probably is. Does the substituent affect the rate of the reaction? And if it does, is it predictable?
What is the E attached to?
The electrophile. Exactly. Where? That's the question. Okay? Where will the electrophile end up? It'll end up on the ring. Will it end up in the ortho position? Will it end up in the meta position? Okay? Or will we get a distribution?
You mean that it's going to like break one of the bonds, though? Is that what it's trying to do?
It's going to do a substitution. So all of our, let me find an example of one. Look, here's an electrophilic substitution, right? This reacts with this, produces a carbocation as an electrophile, and we get this product, and then we end up getting these products. So our reaction is this. Don't forget about these hydrogens, right? Plus some electrophile gives us a substituted product. There it is there. What did it substitute? To balance this reaction now, what else do I need on this side? A hydrogen. What form of hydrogen? A proton, a hydrogen atom, or a hydride ion? If I'm positive on this side, what am I going to be on that side? Am I going to be negative? My charge is net positive. What's it going to be on this side? What's that? It's going to be plus. That's right. So this reaction is now balanced. That's what the electrophilic substitution reaction is. Good question, by the way, because again, Grossman's rule, we forget about these hydrogens. They're there. We're just substituting. We're going to take this off and put that electrophile on. That's why we call it a substitution reaction. We're substituting one of the protons for the electrophile. So that actually is a very good question, right? Because you weren't the only one thinking about that. We forget about those hydrogens. So when we get back to our, here we go. So that's what's happening. There's some hydrogens here. One of these is going to come off as a proton effectively. The reactions we know are a little bit more complicated than that. And this is going to go either in this position here or here. We don't know, and that's the question we're asking. For here, it doesn't matter, because no matter where it goes in the ring, we have a single substituted benzene compound over there. Now, we've actually, we have a substituent here. So on our product, it can go, we can get the ortho product, the meta product, or the para product. Okay, so what we're asking then, is it random where that goes? Probably not. And will the reaction be slower or faster? So we'll answer these questions right away. I know everybody's dying for the answer. Okay, so methylbenzene undergoes nitration 25 times faster than benzene. It's a much faster reaction for this nitration reaction. Nitrobenzene, on the other hand, is 10,000 times slower than benzene for an electrophilic aromatic substitution where we replace a proton with the NO2 group. Okay? We also get poor yields for here. When we take a look at this reaction, we nitrate it, we get all three of these products, okay, but we don't get a statistical distribution. We get 59% in the meta position, in the ortho position, very little in the meta position, and a considerable amount in the para position. Okay? On the other hand, when we do this compound, we get only 6% in the ortho position and 1% in the para position. In this instance, most of it goes to the meta position. So it seems in this one, we're going to find out that substituents are either what we call ortho-para directors. Okay, I would write this down. Substituents will be ortho-para directors or meta-directors. Okay? Now, this is a whole lot faster, and this is a whole lot slower. What do we know about the electronic properties of these two groups? A methyl group. Is it electron donating relative to hydrogen? Remember, in that, we have a methyl group there instead of a hydrogen, so we want to know its electronic properties relative to hydrogen. Is methyl electron donating relative to hydrogen or electron withdrawing? How many people think it's donating? Okay. I want to see a lot of hands, actually. It's donating. Alkyl groups are electron donating. It's inductively, but they're electron donating. They push electron density towards the reaction center relative to hydrogen. Okay? The nitro group, now you have a real good chance of getting this right. How many people think it's electron withdrawing? Okay? It is electron withdrawing. And if we draw a nitro group, whenever we draw a nitro group, okay, typically we draw it like this. So we have a positive charge on the nitrogen. We can suck electron density. We can draw resonance structures where we delocalize these electrons into that nitro group. So we pull electron density away from the ring with nitro groups. Okay? So that helps us now. The rate is easily explained. Alkyl groups are electron donating relative to hydrogen. They push electron density into the ring. This is a nucleophile. It relies on its electrons to attack the electrophile. So if we push more electron density in there, it's going to have more electron density. And that's another thing. We want to think of electrons as these nebulous, spongy liquids, right? We can push more electron density in there, and then it becomes a better nucleophile because it has more electron density. If we have an electron withdrawing group, we're going to suck electron density out of there. It's going to become a poorer nucleophile. So we have a poorer nucleophile. We're making it poorer because this is the part that's the nucleophile on this. And we pull electron density out of there. It's a poorer nucleophile. So this is a better nucleophile. We expect it to attack electrophiles with a faster rate. This is a poorer nucleophile. We expect it to attack electrophiles with a slower rate. And again, here's a little picture that helps us out. Electron donating groups increase the electron density. We're kind of trying to show that pictorially by making these pi systems bigger, okay, spongy liquids. There's more electron density here. In this one, we're sucking the electron density out, so we have less electron density. Better nucleophiles, poorer nucleophiles. Okay, so that explains the rate. What about the regiochemistry? So now we're going to draw a whole bunch of resonance structures, which you guys should be able to draw. So here is what we would, if we attacked at this carbon, these electrons attack our NO2 plus, right? And we end up, that's the first thing the first resonance structure we would probably get. We can draw these three different resonance structures, okay? So let's do the same thing for the ortho and the para position. So once we do that, we're going to look at the resonance contributors, for the resultant iridium cations for each regioisomer, and are any particularly good or bad contributors. Notice I put good in bold here. We put an electron donating group. We're probably looking for things that become better nucleophiles. So in the meta position, we have our resonance structures. I'm going to pretend each one is an individual carbocation. If there is no resonance, that would be a secondary carbocation. That would be a secondary carbocation. And that would be a secondary carbocation. None of these we would think of contributing significantly more to the overall structure than the other. They're all the same. What about if we attack where we would get the ortho position? So now we're putting our NO2 group there. This is the resultant cation. It's a secondary cation. This is a secondary cation. Tertiary cation, more stable, right? Okay, so we would expect this to be a more stable intermediate. So if it's a more stable intermediate, we expect that it's more stable than this one because we don't get any stabilization here. What we're going to find is we get the same thing happening with the para-isomer. One of the resonance structure ends up being more stabilized than the other two. So these ones contribute more. The ortho and para-substituted cations are more stable than the meta-substituted cation. Let's now think of an energy profile for this reaction, okay? So we're going to have either benzene reacting with the electrophile. It goes through some transition state and gives us this intermediate. Now we've already said that the electron donation is going to stable those because we're pushing electron density relative to hydrogen. So we expect all of these to be lower in energy. Here's the secondary one. It's lower in energy only because we're pushing a little bit of electron density. We don't expect it to be a lot lower, but a little bit lower. But these ones where we can draw the tertiary carbocations, we expect to be really much more stable. So these intermediates much more stable. That drags down the transition states as well. So these are going to form faster. So we should get attack at the ortho-para position faster than attack at the meta position. And both of these we expect to be faster than if it was benzene. Okay? So at this point, there's a choice, and the electrophile adds either there or there. That's the lowest energy pathway. If the ends there, it's a higher energy pathway. It would still be faster than benzene, but not as fast as this. And that's why we get a preferred regiochemical outcome where the electrophile goes in either the ortho or para position. So electron donating groups are activating and ortho-para directing. Now let's take a look for electron withdrawing groups. I didn't get my, pretend this one isn't here so you can be surprised when I put it up. Okay, so for the meta position, again, secondary, secondary, secondary. That's fine. Now, let's look at the resonance contributors for the resultant uranium cations, and we're going to look for any particularly good or bad contributors. Now, this is not really a tertiary carbocation because it's not 3 carbons attached to it. There's a carbon, and a very electron withdrawing group attached directly to the positive center. Go back to this resonance structure. If we have a positive center here, and our positive center there, there's going to be a lot of charge unhappiness, right? Positive charges don't like to get pushed towards other positive charges. So this is a particularly poor resonance contributor. And the same thing happens down here in the para position. We get a particularly poor resonance contributor. So in this, because we have one of the resonance structures is a bad resonance structure, that's going to raise the energy of that whole uranium cation. It's going to be higher in energy than if we put it in the meta position. Now we still have an electron withdrawing group, so this is going to be higher in energy than just the benzenium, where we'd have no substitution on our starting material. So the ortho and para substituted cations are less stable than the meta state substituted cation. Let's take a look at what that does. Okay, same sort of analysis. We form, there's our benzenium. As soon as we put an electron withdrawing group, we destabilize it a little bit. Okay? We destabilize the meta, but the ortho and para are even further destabilized. They're even higher in energy. They're going to be the least likely to form. And that's why in this reaction it's slower. We have to push it. Okay? We either have to wait a while longer or we have to go at a higher temperature. We need to push this reaction relative to the other one. But we can make it happen, and we're going to get mostly the meta substituted. Remember, this is a different reaction in blue, so we don't have to worry about that. Okay? This is just trying to show you a little bit about the iridium ions. The structure on the left is iridium cation formed by addition of bromonium to toluene. So toluene, notice now what we're trying to show is that this is a little bit less blue, so there's the positive charge is not quite as concentrated. Now on the structure on the right, we have a lot more positive charge in the ring. It's going to be a crappier nucleophile, and this is formed by the addition of bromonium to trifluoromethylbenzene. Trifluoromethyl is a very electron withdrawing group. So let's do one final little thought experiment. Oh, I didn't get my animations. As you can tell, I made these last night. The best, not the best, but we can imagine that here's our benzene. We're going to substitute on that. I should have put H's there, but we're going to put on there a CH2 minus group. We have what we call the benzyl anion. And we can draw different resonance structures for this. We can push the electrons, right? We can push 2 down there and push 1 over to there. We can keep our arrow pushing, and we can get all the way over to here. So this is just resonance. The real structure, something like this, and look at where all the negative charges are, okay? We've made it a better nucleophile, and where are the most nucleophilic sites? Where those red arrows are pointing. This site as well, but we're looking for electrophilic aromatic substitution on the ring. These are the most reactive sites in this thought experiment. So it shouldn't be surprising that those sites that are the most nucleophilic end up attacking the electrophile, and that explains the regiochemistry, both the regiochemistry and the enhancement of the rate. This is a slightly different analysis than we just did, but it coincides. It gives us the same answers. So notice where the partial charges are located. We would expect they would be the most nucleophilic sites. We can do the same thought experiment, except we're going to put an electron withdrawing group on there. And this time we're going to put a CH2 group on there. CH2 plus group, I'm sorry. And we can, in fact, do the same thing. Our arrows are going in the opposite directions, but we actually can delocalize the charges to the same places. Now we're just going to get from this structure to this structure, we're just going to push these electrons up here and make this a carbon double bond. Then we're going to have our positive charge there like we do in this. And then we can continue to push our electrons around, see the same thing. We get the same thing, our positive charge is delocalized. Look where it ends up being delocalized. Do we expect those positively charged sites to be the most nucleophilic? Or do we expect them to be crappy nucleophiles? Something that's electron deficient, like a cation, is not going to be a very good nucleophile because it needs electrons and it doesn't have them. Okay? So these sites are the least nucleophilic sites. These sites are slightly better nucleophilic sites. So we would expect they would be the least nucleophilic sites here. And that explains why the meta position is more reactive than the other. Now, don't forget Grossman's rule. Some of you, I suppose, are probably thinking, what about this site? Why is it not nucleophilic? Remember, there's another hydrogen atom there. That's sp. I'm sorry. No, that's not correct. But that would end up giving us a different intermediate that wouldn't make sense, because we couldn't pull off our proton from that intermediate. What about chlorine as a substituent? Chlorine's a little different. Chlorine undergoes nitration 30 times slower than benzene. That makes some sense. Chlorine's quite electronegative. It sucks electron density away. So what would we predict for our product yields? we might predict that we would get that this thing would be a meta-director, but it's not. It's an ortho-para-director. So hopefully, most of you are like Chem Baby here, and you're saying, what's going on here? Are you serious? How is it chlorine is deactivating, yet ortho-para-directing? Okay? That's not what we expect. We found out that activating groups were ortho-para-directors, and deactivating groups were meta-directors. So, how do we explain that? We go back to drawing resonance structures. Halogens are inductively electron withdrawing, but they do have these lone pairs of electrons, right? That can contribute through resonance to delocalize that charge. And we can end up delocalizing the charge. We can draw similar resonance structures for the para isomer, but not the meta, okay? So this one and these are the only ones. The halogens are the only ones that are nebulous. They're deactivating, yet ortho-para directors. And it's nice. We can draw a nice little chart. So what happens here? Both of them end up destabilizing the cations that are formed, but the meta one is destabilized even more than the ortho and para ones because of these resonance structures. That's why it's an ortho-para director. So here's a classification for all of our substituents. We actually should be able to figure this out on our own by now. We should be getting to the point where we can tell that things that have lone pairs of electrons in 2p orbitals should be very good electron donators through resonance, right? We're used to pushing the arrows from oxygen to a positive site and then the positive charge ending up on oxygen. The same with nitrogen, right? We're used to seeing structures like this. So where we're pushing that lone pair of electrons in there. They're very good electron donating groups, and they donate through resonance. The amide is less good because those electrons are tied up in this whole functionality here. We actually can draw a resonance structure that delocalizes electrons all the way up to the oxygen. So amides are less good. Esters even less so. Phenyl group is slightly electron donating. These things are actually, they're mostly electron withdrawing. They're weakly deactivating, but they are ortho-para directors. So all of these are ortho-para directors. All of these are meta-directors. And now, notice though, when our carbonyl carbon is bonded directly to the aromatic group, it's an electron withdrawing group. Okay? So this group is a slight electron donor when it's the oxygen that's bonded to the ring, but when it's the carbonyl group carbon that's bonded to the ring, it's electron withdrawing. So you should get used to that. These things are very strongly electron withdrawing. The protonated ammonium, because we have a positive charge on the nitrogen. The nitro group we've already seen. Trifluoromethyl, trichloromethyl are both very serious electron withdrawing groups. And that gives us 15 minutes. Next class, you can see I have the beginnings of some notes, and I'm going to be talking about, we're going to start with a little bit more talk about how we can assess a group's electron donating ability relative to other groups. Because we may need to know what are strong electron donors, and if we have to make an assessment, if there's two groups, we have to be able to assess which one is strongly and which one is not. So what I'm going to do